one of the skills you should have as a designer is the ability to look critically at the artifacts that others have designed. And I want to take a closer look at the Spinbrush and use it to illustrate some of the key ideas around cost and around learning and improvement. So first, let's just take a look at the function of the Spinbrush. It has a bristle head here, and if I press the start button, you can see that this element of the head rotates and this element of the head goes up and down. Now, despite the fact that it's called the Spinbrush, the Spinbrush doesn't actually spin. So you can see here, I don't know if you can see or not, but I could, if it spun, I couldn't do that, right? But indeed, instead of spinning, what it does is it rotates back and forth. So the first thing I want you to think about is, what would you guess you're going to see inside this artifact when I open it up? You have here a back and forth motion, and actually you can see there that the motion of the head is tied to the motion of the lower part of that bristle. So those are tied together in some way. And so clearly there's some source of power, and there's some kind of mechanism that connects the source of power to that head. So let's take a look and see what's there. Actually, the first thing let's do, let's take the head off, which is removable. And we can see here that there's some kind of shaft, and if I look really carefully, I believe that is going up and down. Yes, indeed, that is what's happening. That shaft is going up and down. And I don't think it's spinning, but we'll be able to find out when we take it apart. Okay, so down in the head, there is an element that engages with that shaft. And that has some spring action. So if I push, you can see that I'm pushing with the screwdriver, and there's some spring action that returns it. And so effectively what this is doing is going up and down in order to cause this little guy to rotate and the lower elements of the bristles to go up and down. Okay, now we could pull this apart and see if we can understand what's going on in there. I've obviously made a mess of this, and I won't be putting it back together, obviously, but the way this works is there was a little shaft here that was sitting in that hole, and the back side of the bristle was turning on that shaft. And then what you've got here is just a little arm, and that little arm, when it goes up and down, exerts a little crank action on the side of that bristle to cause it to rotate up and down. So there's a little arm that's basically just going up and down that causes that head to rotate up and back. And now if we cut the top off of that, we can see that there was a little spring that was providing the return action. So in sum, the head of this toothbrush, there's a shaft, there's essentially a vertical shaft here that has a spring on it that goes up through the head that connects to a little arm, and that little arm, as it goes up and down, will cause the upper part of the head to rotate on that little shaft, which is fit into that pivot point on the back of the head. And then just along the way, that shaft will move the bottom part of the bristles up and down. All right? So that's all a pretty complex little mechanism that is up in the head of the spin brush. And what's remarkable is that that mechanism is made in quantities of probably about, certainly in the millions a year, probably in the tens of millions a year. And so as a result, it's made with processes that are largely irreversible. That is, you can't take it apart and put it back together. It's made with processes that basically squeeze and melt and bond the pieces together into an integrated assembly. Okay, now let's see if we can figure out what's going on inside the handle. We know that basically all of the mechanical action that converted that up and down motion to the rotating of the bristle was happening in the head. So there must be something that connects the source of power to that up and down motion. So let's take a look at what we'll find inside. Actually, before we do that, I want you to think about what is it that I'm likely to find inside here? What is it that's going to cause the motion, and how is that motion going to be translated into an up and down action? So the first thing we notice is that there are two alkaline batteries, two so-called AA batteries. They're held in place with a little plastic cap that has what's called an O-ring. An O-ring is just a little rubber, a little loop of rubber, kind of like a rubber band. That's why it's called an O-ring. And it's got a little grease on it to seal it. And that O-ring goes on that cap, and that keeps it sealed against water and so forth around the sink. And then down in the bottom of that cap, there's essentially just a piece of wire, coiled wire, that I probably can't quite pull out, but a piece of coiled wire that just connects the two ends of the battery. Okay, now, as I said, this device is made in quantities of probably tens of millions, and as a result, it's put together with these processes that are not really reversible. So in particular, this is called a clamshell design. It has an upper half and a lower half. The upper and lower half are what's called ultrasonically welded together, which basically means there's a little tool that puts the two pieces together, vibrates them at very high frequency until the joint between them essentially fuses together and melts, and that causes the two pieces to be stuck together. So as a result, I'm going to need to clip this destructively in order to get it open. Okay, so now if we get it open, we can see that there's what we've got going on here. There's a little motor sitting right here, and that motor is powered by the batteries that were sitting there, that were contacted there. And then the switch is back here, which actuates makes a contact that allows that circuit to be completed. And then what we've got here is what's called a pinion gear. Just the little gear at the top of that motor comes right off the motor shaft and turns that little wheel. And that little wheel has a little arm on it here, a crank arm, that's mounted slightly off center, so that when that wheel rotates, let's see if we can get it to do it. When that wheel rotates, that little arm goes up and down, and that's called a crank. And that's what you see, for instance, on the side of an old-style locomotive, or what you see that connects a piston to a crankshaft in an internal combustion engine. And just that little motion of that little wheel causes the up and down motion that again goes through a little seal and up into the top of the spin brush. Now, the reason that that little gear is needed there is the motor wants to spin at maybe 5,000 to 10,000 revolutions per minute, and you want the head on the toothbrush to be spinning much more slowly, and so you need to reduce the speed of the motor, it looks like, by a factor of about 5 to 1 before it gets to the up and down motion of the shaft. There are 4 little screws, and these screws hold the motor in place. It's a little unusual to have screws in something that you're going to make 10 million of, because there's quite a bit of labor, about 5 or 6 seconds usually to put in each screw. And this assembly is done by hand. And then you can see, so there's the motor, there's a little connection. This is the motor shaft, and you can see that little offset. So you can see what you've got now. What I've got now is basically a pile of parts, and this is essentially the total contents of the Spinbrush. And I'm going to just categorize these parts because it's a way you think about cost and manufacturing cost, which is they're exactly 2, maybe 4, but I would argue probably 2 parts here that are what are called catalog items, meaning this is exactly the same component that you could buy in a store to put in a portable music player or a camera or a remote control. It's 2 AA alkaline batteries manufactured by the company Duracell. Maybe these 2 O-rings are standard, but they are probably, even these O-rings are probably manufactured to Church & Dwight's specifications. Everything else you see here is custom. That is, it was designed specifically for this product. And even the motor, so this is a little permanent magnet DC motor. It was probably made by a large, on a machine that was provided by a large company, probably by a company called Mabuchi, although I don't know. They make most of the small motors in the world. And but this motor was custom for this product, designed custom for this product. These little screws, maybe these 3 screws are standard, but even these screws are probably specified as custom for this product. And then these little shafts and this little screw, these little metal bits are all custom. And then all of these parts are injection molded parts, which means they're formed by taking a plastic material, pellets of plastic, melting them and squirting them into a mold in an automated machine that does that on a cycle of about 30 or 40 seconds that spits out several parts on each cycle. So the vast majority of the parts in this product are custom parts. They're designed for this particular product. And the costs here, if you think about it, the costs of this artifact are dominated by the cost of the materials that go into this, and then the costs of the standard components that are purchased and that go into it. In another module, I'm going to go through a spreadsheet in which I estimate what those costs are for this particular object.